Imagine a future where a simple implant could help paralyzed people walk again. That future might be closer than we think. In a groundbreaking study, scientists have developed a spinal cord implant that helped paralyzed rats regain their ability to walk. And now the world is watching to see if humans are next. In this video, we're diving into how the technology works, what makes this breakthrough different, and how close we are to seeing it used in real-world spinal cord injury treatments. Make sure to stick around, because this story could change lives. At the heart of this groundbreaking development is a bioelectric spinal implant, an ultra-thin, flexible strip of biocompatible material designed to be placed directly at the site of spinal cord injury. Rather than attempting to manually reconstruct or surgically bypass the damaged area, this implant works by restarting communication between the brain and the body, using precisely tuned electrical signals. Developed by a collaboration between the University of Auckland in New Zealand and Chalmers University of Technology in Sweden, the implant emits a low-frequency 2 Hz electric field directly into the injured spinal cord tissue. This isn't just random electrical stimulation. The frequency and positioning are carefully calibrated to promote axon regeneration, the regrowth of nerve fibers that carry signals between the brain and the limbs. When the spinal cord is damaged, these axons are often severed or silenced, making it impossible for the brain to send commands to muscles. What this implant does is create a favorable environment for these axons to reconnect and grow, restoring that vital neural traffic. It's like rebuilding a destroyed highway between two cities, except the cities are your brain and your legs. One of the most revolutionary aspects of this device is its physical composition. Unlike traditional spinal implants made from rigid materials that can aggravate or inflame surrounding tissues, this one is made of a soft, stretchable material that conforms naturally to the spinal cord's shape and movement. It maintains full, stable contact with the injury site without triggering the immune system or causing secondary damage, something that has plagued other implant designs in the past. Another critical advantage, it's minimally invasive and doesn't require large power systems or external machinery. It can function autonomously, which could allow for longer-term implantation without the need for constant monitoring or battery swaps. This simplicity and stability are what give the implant serious potential for real-world, human application, not just in labs, but in hospitals and rehab clinics down the road. To test the implant, scientists induced partial spinal cord paralysis in laboratory rats, simulating the kind of damage seen in real-world spinal injuries. Once the implant was placed over the damaged spinal area and the electric field was activated, the results were astonishing. Within just 4 weeks, the rats that had previously lost use of their hind legs began regaining voluntary motor function. What's particularly remarkable is that the recovery wasn't limited to just movement. In several of the treated rats, researchers also observed the return of light touch sensation, indicating not just motor recovery but also sensory signal restoration, a key factor for complex tasks like walking on uneven ground or reacting to pain and pressure. This dual restoration is critical because coordinated walking requires both the ability to move muscles and the ability to feel feedback from the limbs. Even more encouraging, the outcomes weren't isolated. The same results were consistently observed across multiple test animals. The implants caused no inflammation, no rejection, and no toxicity, all of which are major hurdles for any implantable medical device. This suggests not only that the technology is effective, but that it's also biologically safe over time. Importantly, the movements recorded weren't just reflexive or involuntary muscle twitches caused by electrical stimulation. The rats demonstrated purposeful, coordinated walking behavior, which indicates that the implant had successfully reestablished functional communication between the brain and the spinal cord. That's a huge milestone. These findings, published in the prestigious journal Nature Communications, have triggered immediate interest across the neuroscience and medical communities. While there is still a long way to go before we see this used in people, the strength and consistency of these results suggest that we may be witnessing the early stages of a transformative medical breakthrough, a new era where paralysis may no longer be permanent. Spinal cord injury research has certainly made strides over the past few decades, but despite the buzz surrounding many experimental technologies, very few solutions have successfully moved beyond the lab into widespread clinical use. Historically, treatments have leaned heavily on mechanical support systems like exoskeletons, robotic braces, or functional electrical stimulation devices that help paralyzed patients move their limbs using pre-programmed patterns. While impressive, these systems generally don't restore actual neural function. They assist movement but don't repair the damaged spinal cord or reconnect it to the brain. In other words, they treat the symptom, not the root problem. Patients might regain a level of independence, but not true autonomy or sensation. Attempts to create implantable devices have also faced serious hurdles. Many used rigid or semi-rigid components that didn't conform well to the flexible, delicate tissue of the spinal cord. Over time, these implants often caused friction, swelling, or even immune responses that led to rejection or failure. This made them unsuitable for long-term use or left patients worse off than before. The new bioelectric implant changes that equation. Its soft, ultra-flexible design avoids those mechanical pitfalls, allowing it to mold seamlessly around the spinal cord and maintain uninterrupted, safe contact with the nerves. More importantly, it's not just restoring movement, it's also restoring sensory feedback, such as the feeling of light touch. That's something most previous approaches never achieved. Real walking is not just about moving muscles. It's a finely tuned feedback loop between what your body does and what it feels. Imagine walking on gravel barefoot. You need to feel each pressure point to adjust your gait. Without that feedback, you risk injury or collapse. That's why this implant's dual action, restoring both motor control and sensory perception, is such a major leap forward. And because of its low complexity, scalability, and compatibility with existing surgical methods, this technology isn't limited to treating new injuries. It could be adapted to help people living with long-term paralysis, spinal degeneration, or even diseases like multiple sclerosis, where nerve signaling breaks down over time. In short, this isn't just another prototype. It's a potentially universal platform for neural repair. Right now, the implant's success has only been demonstrated in lab animals, but the long-term mission is crystal clear: translation into human treatment. Researchers are currently focused on fine-tuning the implant's electrical output, size, and response patterns in rats, but they're already planning how to scale the system up for the much more complex human nervous system. The challenge isn't just that human spinal cords are larger, it's that every injury is unique. Some injuries involve total severance of the cord, others are partial or involve scarring, and they can occur at different levels of the spine. That means the implant will need to be adaptable, able to vary the shape, power, and stimulation pattern depending on the patient's specific condition. There's also the reality of regulation. In most countries, an implantable device like this must pass rigorous preclinical testing, followed by multiple phases of human clinical trials, which can take years. These trials need to demonstrate not just efficacy, but long-term safety and biocompatibility across a wide population. That said, this implant has a big head start. Its non-invasive nature and minimal risk profile make it far more likely to gain ethical approval for testing than many previous attempts. Beyond the medical hurdles, there's the question of access and cost. To truly revolutionize treatment, the implant must be manufactured at scale and made affordable for spinal cord injury patients, not just offered as a luxury neurotech product. Researchers are aware of this and are working toward a design that could be mass-produced without compromising on precision or safety. It might take 5 to 10 years before this implant becomes an approved therapy, but for the first time, that timeline feels plausible. This is no longer a dream or an outlier experiment. Thanks to this breakthrough, the idea that a person with spinal cord damage could regain mobility is moving out of science fiction and into medical reality. While this discovery is exciting, it's important to acknowledge the challenges ahead. First, there's the issue of individual variability. No two spinal cord injuries are exactly the same, and results may differ between patients. What works on a rat may not be a silver bullet for humans. There's also the cost and accessibility question. Cutting-edge implants like this could be expensive when first released. Ensuring that patients worldwide can benefit, not just those with deep pockets, will be a major concern. Ethically, researchers must also ensure that human trials are conducted safely and responsibly. With so much at stake, patient safety must be prioritized over speed or hype. Still, if this implant continues to show positive results, it could transform the way we approach spinal cord injuries, and maybe even other neurological disorders. So, could paralyzed humans walk again thanks to this implant? The early signs are promising, but we're still in the early stages. What's exciting is that this breakthrough gives us a real glimpse of what the future of medical technology could look like. A world where spinal cord injuries are no longer a life sentence. Whether you're passionate about neuroscience, medical innovation, or future tech, this story is one to watch. The next few years could be pivotal in turning hope into healing. Make sure to subscribe to Tech on the Mind for more future-shaping tech stories, and leave a comment. What do you think about this breakthrough? Are we getting closer to reversing paralysis?